Understanding the three types of radiation is certainly useful, but what we need to understand to go to a deeper level is the two different types of nuclear reactions. The first type is called nuclear fission, and the second type we'll get to in a little while is called nuclear fusion. So nuclear fission is the splitting of a nucleus into basically two fragments of approximately the same mass. So you're going to take a large nucleus, you're going to bombard it with a neutron, that'll break it apart, and then those will then make two smaller atoms of about the same mass, and then also releasing, more neutrons. Okay, so it occurs when a fast moving or rapidly moving neutron collides with a larger nucleus. The process produces excess neutrons, each of which would go on to split another nuclei, and then those would go on to split more nuclei, and this is called a chain reaction. So the best way to show you what I'm talking about is if I just show you the image I attached below. So in this particular image, we have uranium-235 at the far left. It's being bombarded by a neutron right here. And as it hits that, it's going to break it apart. Again, as long as it's moving fast enough, notice it's going to make two similar sized. This is 140 mass and 93 mass, or krypton and barium. When those split, that's going to release another three neutrons. Those neutrons then can split some more uraniums, and then that would again produce rubidium or cesium, strontium or xenon or bromine or lanthanum. Again, those are just examples, just got to give you an idea that it's not an exact fission for every single uranium-235. But again, what I also want you to notice is that we have neutrons being released, and then those neutrons can go on and interact with other nuclei of uranium-235. Again, what I also want to point your attention to is the energy release here. The release of energy is really important because that, again, is what we're going to harness in order to make fission a useful reaction for us. All right, now that we understand what a chain reaction is, again, like it says here, there's a tremendous amount of energy are produced in fission reactions. This is why we use them for power plants. There's something called a critical mass. A critical mass is the amount of material that you have to have in order for a chain reaction to start. If you have a mass of your fissile material, to use the word, or radioactive, like say uranium or plutonium or whatever it may be, but we don't have enough of it, like literally we don't have enough mass, then a chain reaction just cannot occur. We have to have a sufficient quantity of it so that once those neutrons start bombarding and bombarding and bombarding, it's just going to go on and go on and go on and go on and go on. That's called a chain reaction, and again is only attainable once we reach a critical mass. Anything below that, it's not going to go on as a chain reaction. All right, so these fission reactions are used in atomic bombs. They will also use them in our nuclear reactors. Whenever we talk about nuclear power plants, we are always talking about fission reactors. Now, the way they work is we have something called fuel rods. Fuel rods, I'll show you what those look like in a second. They're usually very, very highly enriched uranium-235 or plutonium-239. We enrich them by spinning them in high-powered centrifuges under a vacuum where they're spinning so fast that the radioactive isotope is actually pushed against the wall, whereas the slightly lighter non-radioactive or non-isotope of uranium gets pushed closer in. So we're separated by, we're talking about neutrons. That's how fast we have to spin it. Whenever we're talking about countries trying to enrich uranium or something like that, say Iran or some other countries where they're trying to get nuclear weapons, North Korea, one of the ways that we could measure their progress is by their centrifuges. The more powerful centrifuges they have, then we know that they can enrich uranium and plutonium to a much higher degree because they have to spin, like I said, so incredibly fast under a vacuum to literally separate atoms based on one or two neutrons. It's pretty remarkable. Again, also in a metal, not in a liquid state, in a metal state. So that's how fast we have to spin. All right, in order to control, once we attain critical mass and where chain reaction is about to begin, we need something called control rods. Control rods control the rate of a reaction by absorbing the neutrons. So if the neutrons are being created and then they're going out and being multiplied and going out and then bombarding other nuclei. If we could insert a control rod into that reaction and absorb the neutrons, then that would in effect slow down the rate of reaction, because if we could absorb neutrons, then therefore they're not going to have the opportunity to bombard other nuclei and to keep that chain reaction going. So you'll see in a minute when we're talking about nuclear reactors is we have control rods that literally we raise and lower into the nuclear reactor to either speed up the reaction or slow down the reaction by absorbing, or I should say absorbing or not absorbing neutrons to again influence the rate of the nuclear fission reaction. Now there are some significant problems with nuclear fission reactors. One is that fuel must be mined from the ground. Okay, and so that's going to disrupt the ground, of course. And also the uranium and the plutonium that we get is typically from countries over in the Southeast Asia and places that are not always, well, it's hard to describe. Let's just say they're not always countries that are super, super friendly. These are not our closest allies, say Germany, England, France, places like that. These are countries that are not by any means adversarial, but it's more complicated. Again, we have to get it out of the ground. We have to get it all the way over here back to the US. We have to enrich it. There's a lot of money that goes into this, and mining is not easy. The second one is fission reactors produce very large amounts of nuclear waste. So nuclear waste, again, is going to stay radioactive for a very, very long time. And we don't really have anything to do with it or to do to it because there is nothing you can do to it. Once you have nuclear waste, it must decay. And you'll learn later that there is no way to increase or decrease the rate of decay. It's just a natural process. And the only way we could take care of it is to store it and then allow it to have the time to decay at its natural rate, which again, we cannot speed up or slow down. So like it says in number 3, everybody knows that we need to store it safely and we need to keep it safe. And so we build mines underneath mountains and salt caverns. We do all sorts of very interesting things. There's talks of shooting it off into space. I mean, there's all sorts of ideas of what we could do. But nevertheless, it's always going to be radioactive for thousands and thousands of years. But there's an old saying that says, not in my backyard, meaning I understand that we need to do this, but just don't put it near my house. You could put it near anywhere else, just not near my house. And that's a common problem with nuclear waste is, like I said, it's a known problem. There's not a whole lot we could do other than store it safely. But who really wants this near their house? Understandably so, right? All right, let's talk a little bit about, again, how the nuclear reactors work in a little bit more detail. All right, so what you guys can see here is we have a fuel pellet, which is shown over here far on the right side. A fuel pellet is very small. Here it is. It's about as a part of your little pinky. And then we stack them into one of these, what we call a fuel rod. We just talked about that. These fuel rods, again, are going to make the nuclear power. So there's a whole bunch of those, dozens, if not hundreds of them stacked, very small nuclear pellets. And then these fuel rods are then assembled into a fuel assembly where they're all held together like this. And then what these are going to do is as they naturally decay, as the uranium or the plutonium in that fuel pellet naturally decays, it's going to create an abundance of heat, not just energy, but also heat. Now, why this is important and why this is useful for us as humankind is because for each one of these little itsy bitsy pellets, like it says about the size of your fingertip, that's about 17,000 cubic feet of natural gas. That's a lot. 149 gallons of fuel or a full ton of coal. So for something about this size, we're getting that much energy. So there's a lot of benefits to nuclear power in that it doesn't produce greenhouse gases. It doesn't produce anything into the air other than water vapor, and we're getting a great amount of energy out of this. There are some drawbacks, of course, though. All right, so the way the nuclear reactor works in a little general schematic here is we have a nuclear reactor over here on the left. So the nuclear reactor, you guys can see the fuel rods right there. You guys can see the control rods that we would raise and lower into that reactor to, if we lower it, again, it's going to slow it down by absorbing neutrons. If we raise it up, we're going to not absorb the neutrons, therefore increase the rate of the reaction. What we're doing basically is something quite interesting because this is, again, basically 1800s technology from here on out. what we're doing is we're going to pump water into the reactor. The radioactive decay will heat this water up to be very, very hot. And then we're going to pump it into a steam generator. By the water that is inside this tube, shown as red, is very, very hot. Then we're going to have a steam generator where we have cold water. When we have hot water inside the tube and cold water outside the tube, what you get is a boiling, which would make steam pressure. The steam will rise. The steam will go into a turbine. The turbine will spin, 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 spin. That spinning will generate electricity thanks to a generator, and that will be shipped out to nearby cities. Meanwhile, that steam, excuse me, that steam is going to go down into a steam condenser. So now it's the opposite of a steam generator. Basically, what we're going to do is we're going to take cold water. The cold water will go inside the coil. And as the cold water comes in contact with the steam, shown as the light blue, it will then condensate back into the liquid state. And then that liquid will be then pumped right back into the steam generator. So basically, again, we have two closed loops. We have a closed loop, which is this right here. That's a closed loop where the water is just heated up and is continually heated. But as it goes into the steam generator, it's cooled down a little bit because, of course, the heat flow would go into making steam. The second closed loop is going to be this one right here. As we're going through here, we're making steam, and then we're condensing it back into liquid, and then we're making steam, and then we're condensing it back into liquid, and then we're making steam, and condensing it back into liquid, and so on. And again, in the process, spinning this turbine to make electricity. The only thing that is not a closed loop is going to be this right here. This is going to come from a cooling lake, typically, and then as it's coming in from the lake, it'll get heated up as it cools down the steam, turning it back into a liquid. It absorbs the heat, and then it has to be released into the air as a big white cloud. People sometimes confuse this as pollution. It is nothing more than steam, and a lot of it. So it's a beautiful white cloud. There's nothing toxic about it whatsoever. There's nothing poisonous. It's not damaging the environment. The only problem about this entire process, again, that has some drawbacks, again, is these fuel rods. Is what do we do with these after they've been used? That's the question. Everything else is a perfectly self-sustaining, very simplistic 1800s technology, but we're adding a nuclear reaction in order to heat it up, as opposed to, say, burning coal, natural gas, diesel fuel, or something like that. So that's the general idea of it. Here we have a little bit more complicated. It's all basically the same thing. The only thing I want to show you guys that is an addition to what I just showed you is the reactor core typically has a very, very strong cap on top. And that would be just in case there is a problem. We want all the radiation to be contained in here. Let's just say something bad happens. So it's a very strong cap here. And then notice again, like it says right here, we're gonna have walls made of concrete and steel, typically 3 to 5 feet thick. So if this doesn't hold, and this is ruptured, say in the event of a catastrophe, then the radiation may escape, but it should be blocked and held in by this concrete containment dome. So everything else, like I said, is pretty much the same. I just wanted to show you guys some of the protection mechanisms that go into operating nuclear power on a more safe, way.